Today's lecture deals with oscillation of a spring, an application problem on differential equations. Suppose the spring is fixed at the point O. Observe clearly, this is the point O where the spring is fixed. Mass M is fixed at the point A. Since the mass is fixed at the point A, automatically the mass will be stretched to the point B because of spring action. Right? The weight of the mass is more, so therefore it will come to the point B. Now this mass is in equilibrium position. This mass, which it was at A, now it has come to the point B. It is in equilibrium position. When it is in equilibrium position? When two forces are equal. What is the one force? The one force is the force which is acting downwards, given by mg. That is acceleration due to gravity, mg. What is the another force? The another force is, one force is acting downwards, that is mg. Another force is the restoring force acting upwards. The restoring force is given by k into E, because the distance AB is E. Because the distance AB is E, k is spring constant. That k into this distance, right? Observe, what is the distance AB? E. That E into spring constant k, this will be the restoring force. So two forces are there. Now observe the point very clearly. When the mass M is fixed at the point A, it due to weight, it comes to the point B. Now the mass is in equilibrium position. Since it is in equilibrium position, two forces must be equal. One force is mg, which is acting downwards, that I have written here. What is the other force? Restoring force, which is acting upwards. That restoring force is k into E. How I got k into E? K is the spring constant. E is this distance AB. Next, when the motion is induced, observe the point. This is before motion is induced. It is in equilibrium position. When the motion is induced, this mass B, which was at B, it comes to the point P. Here I am showing that. Same figure I have written. A here B, same thing. This comes to the point P, right? Why? The motion is induced, so therefore the point B comes and sits at the point P. Now what is this distance AP? This distance AP is nothing but this AB. The distance AP, it is equal to this AB plus BP. What is AB? AB is equal to E. What is BP? BP is equal to X. Second point, if this mass, whatever is attached, it is subjected to a damping force given by R into dx by dt. This force always acts upwards. mg acts downwards. Damping force acts upwards. Next, if the point O, this point O, is subjected to an external periodic force given by mp cos nt. So clearly understand what are the forces acting. The force acting is one, acceleration due to gravity mg. Another one, damping force R into dx by dt acting upwards. Damping force R into dx by dt, which is acting upwards. Another force, periodic force mp cos nt. That means the point O is vibrating with a periodic force mp cos nt. When this is the situation, how will be the differential equation? So here the important point you have to understand, before motion is induced, at the point B, the mass is in equilibrium. Why it is in equilibrium? Because two forces must be equal. One force is mg, acting downwards. What is the other force? Restoring force acting upwards. Restoring force is ke. The acceleration due to gravity is mg, therefore mg is equal to ke. That is one point you have to understand. Second, when motion is induced, this point B comes to the point P. Now what is the distance AP? AP is equal to AB plus BP. What is AB? AB is equal to E I have given. What is BP? BP is equal to X. Next, remember the forces what are acting. One force is mg acting downwards. Another force is damping force R into dx by dt. When the mass m is subjected to a damping force, then it is given by R into dx by dt. Also this point O is vibrating with periodic force mp cos nt. Then what is the differential equation? The differential equation is F is equal to me. That is m into d squared x by dt square. Is A is d squared x by dt square. M I have written that as it is. That is equal to, what is the force acting downwards? One is acceleration due to gravity mg plus second one restoring force. Restoring force means AP. Now earlier I told you AB because the mass it was at B. Now the mass B it has come to this point P. So what is the distance AP? It is given by E plus X, that AP into restoring force plus damping force which is acting upwards, restoring force spring action upwards, so therefore acting upwards. Next periodic force, so therefore mg write that as it is. AP it is E plus X, I have written that, into restoring force acting upwards, spring action upwards, so therefore minus K, E plus X into minus K. Damping force it always acts upwards, right? Dampers are fixed to the building in order to prevent the earthquake. It avoids, it acts against the downward force. So damping force upwards, so therefore minus R into dx by dt. I have already told you damping force is R into dx by dt, I told you. But when it acts upwards, minus R into dx by dt plus periodic force, that means the point O, when it is vibrating with a periodic force, it is given by mp cos nt. So this is the differential equation corresponding to the oscillation of a spring when the mass is subjected to some damping force and periodic force mp cos nt. Suppose if I want to remove this periodic force, this term you are removing. If I don't want periodic force, remove mp cos nt. If I don't want to fix a damper, remove minus R into dx by dt. Then this will be the situation. Now also note the point, mg is equal to ke. So here mg is equal to ke, this mg and this ke cancels, then what remains? X only, x into minus k. Mg is equal to k into e, this mg, k into e cancels, so minus k into x remains. I have shown it here. Mg ke cancels here, so minus kx, right? That is remaining, minus R into dx by dt plus mp cos nt. Divide by m, you have this, right? When you divide by m, all terms will divide by m, minus R by m, right? Minus R by m, minus k by m, mp cos nt divided by m means m cancels, so this is what you have. Call this R by m as 2 lambda, this R by m, this one, you call that as 2 lambda, k by m, this k by m, you call that as mu square, then this will be the differential equation. Okay, let us stop at this point.